Yeah, I do birds and flocks, but I don't control them at all. So you may wonder why I'm here, apart from this connection with Bill Bialek, which is probably not enough. Perhaps I wonder too. I hope that at the end of the talk you will have some reason for me being here. Anyway, I think that inviting people from different communities is very important, so I would really like to thank the organizers for inviting me here. So I'm a statistical physicist by training, and now for about 10 years I've been studying this phenomenon. These are starling flocks over the skies in Rome. And in the last 10 years we have learned a couple of things about them, not many. But the only two facts I think you need to know to follow the rest of the talk is that interaction is short range and correlation is long range. Actually, the only relevant information for what follows is that this is a system with short range interaction. So a very basic one in the sense of statistical physics. So every particle, every bird interacts only with a bunch of neighbors, and through the very well-known mechanism of interaction and correlation, there is emergent long-range order. Also, correlations are long-range, on the other hand. So this is a strongly correlated system with short-range interactions. This is the only thing you need to know. Today,
do you see the bird up there?
well, but it's mostly entertainment, so the blue is fine anyway. So what I will try to discuss today is something, is a step further. So we'll try to understand how information propagates across the system, across the flow. And here by information, I will mean how the collective decision to turn, to change the global direction of the flow, propagates across the flow. So very simple kind of information, okay? The final message of the talk will be that in order to transmit information efficiently across a biological network, you need inertia, which is perhaps not so an intuitive concept because we normally associate inertia not to the swift happening of things. But I will convince you, I hope that will convince you that to transfer information efficiently across a biological network, you do need an inertial component in your equations. So the way I study flux is by doing experiments and then trying to build theories over the data. So I will give you a very short glimpse of what I mean by experiments. So we really sit on a roof of different public buildings in Rome. We've been doing this for years to take multi-camera images of the flux. So this is what is called stereometry. Synchronized camera, high definition in space and time cameras. And from the multiple images of the flock of the birds in each camera, you can reconstruct their position. The main problem that you have, though, is the one of occlusions. So you have to transform images like that into data, three-dimensional data. And this is the problem, that sometimes birds can just occlude each other on one of the images, and you have to resolve this ambiguity. Fortunately, you have the other cameras. Actually, we use 3 cameras, not simply 2. And unless they really went one on top of each other in physical 3D space, and if they do that, okay, I don't care, I'm happy to lose the identity. But if they don't do that, I will have 2 different trajectories in the other cameras. So what we need to do, and that was a big part of our work, was to develop a tracking method able to use this information to produce trajectories. Because you see, the problem is that when you have an occlusion here, you risk to get into the blue trajectory than into the green one. So you risk to create wrong trajectories. And the big step forward we did was not to make a choice. So a lot of tracking methods, when they arrive into the occlusion, they make a choice by using some extrapolation to the trajectory in the future. We don't do that. What we do is to produce all possible trajectories. So we have a space of virtual trajectories of the birds, And then we define a probability on this space. And using the constraint of the stereoscopic connection between the cameras, we solve a global assignment problem. So we solve a global optimization problem, and we find out the trajectories in this way. I won't give you the details of that, but this actually we managed to publish this in a specialized journal. Okay, so once you have the trajectories, you can study turns. So this is, for example, one of our real set of data. So this is a flock. This is Jesus, I guess. And so you see here you have a global change of direction. We want to understand how that propagates across the flock. So this is the real data, and this is the three-dimensional reconstruction of that data. So this is not a simulation, it's not a model. This is really the three-dimensional reconstruction of what you just saw. And you see by the change of colors that even at this level, that there is propagation. So the turn originates somewhere here, and then it spreads very quickly to the rest of the flock. Now, this is of course important, because keeping cohesion for these guys is very important, because they are constantly facing predation. A falcon, a peregrine falcon, is always around, actually more than one peregrine falcon. And what is well known is that isolated guys are lost, meaning the falcon always tries to prey on them. And when the falcon attacks the flock, what it tries to do is to split the flock so that some birds remain astray and to concentrate on those. So keeping cohesion while changing direction of motion is a very big issue for a flock. So we want to study this phenomenon. What we do is the following. The turn is basically a bump in the acceleration of the trajectory of the bird, okay, in the centripetal acceleration. So we have all the trajectories, so we can plot the accelerations as a function of time of each bird. And so then what we do is that we take pairs, all possible pairs of birds, and we found the mutual delay, which is, you see, is rather simple. You find the time translation, tau ij, which is the optimal overlap of the two centripetal accelerations, right? So in this way you have not the absolute turning time, which is very ill-defined, because it's very hard to say when the turn started, because not it was going perfectly straight and then started to turn, right? It's a soft phenomenon, but it's very easy to give relative delays. So from all the relative delays, now you have like a tennis ranking, so you have all the matches, and then you can reconstruct the ranking of the birds. So you have the first bird to turn, the second one, and so on. So you have the rank and the turning time delay. So the sixth bird turned 134 milliseconds after the first one. And from this you can start answering questions. The first question is the origin of the turn really localized in space? Because I'm talking about propagation, but it could be something different. For example, if you all have to follow me at some point, the first people to follow me when I clap my hand will not be localized in space. They will scatter around the audience, right? So if the turn is polarized by some external field, you would not expect the first guys, the nucleus of the turn, to be localized in space. So if the turn is being originated by some external factor which affects all the birds, you would expect the nucleus size to grow with the size of the flock. But this does not happen. So the birds which, the first birds in the ranking are always very localized in space. So this is proof that the turn starts locally in space and then it spreads to the rest of the flock. So we can actually ask how does it spread and propagate to the rest of the flock. So what we do then is to build this ranking versus time curve. So here you have a rank of the birds, so the first one to third, the second one, the third one, and so on. And here is the delay after the first one. This curve is very useful because once you have this, you can relate not only rank but space to time and work out the dispersion relation. And how you relate space to time is very easy, because if the origin of the turn is localized, then the rank is trivially connected to space. In other words, if you say that the signal has reached 100 guys, This means that 100, so the rank reached by the signal by that point, must be equal to the density of the flock times the distance covered by the signal cube in 3 dimensions. Okay? Of course, we're assuming isotropy here, which is not necessarily true, but let's say a total 0 is probably true. So then you have a trivial relationship between the space traveled by, the distance traveled by the signal and the rank of the birds reached by the signal. So if you then plot this, what you find in every flock is this kind of curve. So again, these are experimental data in a real flock. This is a rather smallish flock, 76 birds. So what you see is that there is clearly a linear propagation regime. Of course, at the end, you must violate that, because at the end, the signal arrives to the border of the flock, which is finite, of course. So at that point, your assumption of a 3-dimensional isotropic propagation breaks down. So here you have the breakdown of that. But you have a linear regime. So you have linear propagation of the signal. So you can define a speed of propagation, and you can measure that. So we have the speed of propagation of the signal in the flock. All this in the center of mass reference frame. So this has nothing to do with the velocity of the birds. Okay? So the fact that this speed is actually much higher than the speed of the bird itself is, in my opinion, irrelevant. But for some reasons it's relevant for the biologists. But for me, I would say it's completely irrelevant. This is propagation in the center of mass reference frame. So this is really the speed of the signal across the flock. So this is the first information. Information propagates linearly through the flock. The second point is that the attenuation of the signal is very weak. So this again is the centripetal acceleration of many flocks in the rank. So the red ones are the first in the rank, the green the middle rank birds, and the blue the last rank birds. So you see there is some attenuation, but it's not huge. So if you plot the strength of the maximum acceleration as a function of the rank, yes, you have some attenuation, but it's actually very weak. So the signal goes through the flock basically undamped. And again, biologically, this is exactly what you want. Otherwise, you would lose people across this propagation. And finally, what we have is that if you measure the velocity of propagation, the speed of propagation of the signal in several flocks, sometimes, which is the slope of this line, sometimes it's the same, but sometimes it changes. So across all our flocks, we find actually a pretty big variability of the speed of propagation. So this sound speed is not always the same. So it depends on something. And for a long time, we're not able to make sense of what was depending on. So we thought about density, the size of the flock, but we couldn't make sense of that. So it could be just a random number, of course, because it's biology, so this doesn't need to be a law. However, it would be nice if it were. So what does the sound speed depend on? No, the shape doesn't matter. The shape doesn't matter. Okay, so we have to make sense of these three experimental facts. Linear dispersion law, negligible attenuation, and variable speed of propagation. Now regarding the first point, linear propagation seems obvious. Sounds have normal sound, linear propagation, light is linear propagation. However, remember, these are not density waves. These are spin waves, what in physics we call spin waves. Now spin waves, they don't always have linear propagation. We will see that in a minute. So linear propagation of the orientation of the system is not something entirely trivial. Okay, so we have to explain these experimental facts. So let's turn to the, let me call it classic theory of collective behavior. Classic theory, classic because it was formulated by physicists. Probably biologists would object. But the point is that before we started taking data, there were already a large body of models in collective behavior. Biologists started doing that in the 60s, so Kubo, and then the physicists started doing that in the 90s. So very many models in the market, and of course there is the usual duality between physicists and biologists. So biologists tend to give very accurate and detailed models with many parameters. which reproduce the phenomenology very well. Physicists tend to give very simple models with very few parameters, which do not reproduce the phenomenology very well, but at least they can be studied analytically sometimes. So I will analyze one of these models, the first introduced by physicists, but believe me when I tell you that the essence of the model, which is this equation, which is imitation of your neighbors, is pretty much the same across many, many models of collective behavior. So what this equation is telling you is that Vi is my direction of motion, and let's assume here that the speed is constant, so they only change direction. This equation is telling you that the way I change my direction of motion is by averaging the direction of motion of my neighbors. So J belonging to I means some kind of interaction network. I'm not giving details about that, but let's say that you just interact with your nearest neighbors. So what you do is that you integrate the direction of motion of your nearest neighbor, you watch your nearest neighbor, and you try to copy their direction of motion with a strength J. So here there's one relevant parameter, which is the strength of the interaction. Plus noise, of course. Why noise? Because there must be noise. Noise. It cannot be deterministic. These are birds, it's air, a lot of things going on, so there must be noise. Assumption. So I think you agree that this is a very simple model. It's actually also a very successful model. And because if you use this equation, then you have emergent long-range order of flux. So V is the velocity, remember. So there is also another equation I'm not writing here, which is x dot equal V. So then they follow their velocity to move in time and space. It is very useful to rewrite this equation by using a pseudo-Hamiltonian view. So by saying that V dot is minus the derivative of some energy with respect to V. And you see the energy is simply that, because if you derive this, you get this piece here. And why this is useful? Well, because if you're a physicist, this is immediately talking to you about ferromagnetism. So this energy is low, and you want to minimize the energy, statistical physics and the free energy in particular, when Vi and Vj have the same direction. So this is an interaction which tends to produce alignment, okay? But it's just the same thing here. So to make progress, we have to do something technical, which is to do the spin wave expansion. So these are very polarized systems. They're all more or less going in the same direction. So what you can do is to expand around the mean velocity of the group. So to introduce the phase fluctuation, which are small. All these are small fluctuations around the average direction of motion. If you expand for small fluctuation around your order parameter in a soft model, what you have is the classic spin wave expansion. This is way back, Dyson and so on. And what you have is that you can write the same Hamiltonian in terms of these phase fluctuations. Now, I don't give you the details, but look at the final result. It's very easy. You can either maximize the scalar product between the two vectors, or minimize the difference of the phase of the two direction of motion. It's exactly the same. Okay? So it's no surprise that this is equal to that. So now phi I, you can imagine, is the direction of motion of bird I. It's the phase of bird I. And if you go to the continuous limit, this is pretty much the integral of the gradient square of the phase. So it's the good old Gaussian model of field theory. So you want to minimize the difference in direction between birds, which is again to say that you want to have alignment in your system. Okay, so now let's write the same equation here, Vicek equation, in continuum space. So what you have is now phi dot equal minus dh over dphi. This is the Hamiltonian. And if you derive this with respect to phi, the functional derivative, you get the Laplacian of phi. So bottom line, phi dot equal j Laplacian of phi. I'm simplifying a lot here, but the dimensional essence of the problem is this. First derivative in time, second derivative in space. Remember, this right hand here is imitation of your neighbors, okay? But clearly this is not good, because the dispersion relation of this is omega equal ik squared, or if you're not fluent with Fourier analysis, which you are anyway, this means that space scales like the square root of time, not linearly. Plus, this I means that there is dissipation. So this is a dissipative dispersion law with no linear propagation at all. So bottom line, the classic theory does not work. But if you want to see the real thing, not just this simplified equation, I can show you a simulation of the classic theory. So this is a simulation of the classic Zigzag model. The only difference with a normal simulation is that we control the blue bird. So that blue bird is controlled by us. He mimics the fact that he gets some information at some point, and so it will turn at some point, because for some reason, he sees the falcon, he decides to go left. So at some point we turn the blue bird to the left, and we would like this information to propagate to the rest of the flock. So let's see how the classic theory performs. So not very well. It's actually even worse than what I described it to you, because you see, what I told you is that there was diffusive propagation of information, but there's not even that, because the system is active. So when it fails to transfer information quickly, it gets out of the flock. So at that point, there's not even diffusive propagation of information because the system is active. Okay? So this is not good, and this is a total disaster, of course. So you were unsuccessful in transferring information to the whole flock. You created isolated poor guys like this one, who are certainly prey of the falcon. So this is not what we need. Okay, so why the classic theory doesn't work? This is basically the classic theory. Phi dot equal force. Okay, it's not a real force. It's a social force, but it's still a force. It's something that acts on you. And phi is your direction of motion. And there was a first order derivative in time. So this is weird, if you think about it. Because this would allow you to change by 180 degrees your direction of motion in one time step. So the force is directly acting on the first derivative, which is not what you expect. So let's go back to good old Newtonian mechanics. You certainly know about this equation, even if you are not a physicist. So Newton said, no, look, force acts on the acceleration. So we control acceleration, not velocities. We wish we control velocities, but we control accelerations. So how is that? Very often in physics and in biology, even though we start from this equation, we end up here. This is a very general and basic series of slides. It's page 5 and 6 of the book by Swansea on statistical mechanics. So why, if we start from here, we often end up here? Because, I only studied here as an undergraduate student, and then, since when I was a grad student, it was always Langevin equation over damped Langevin equation, phi dot equal, and phi could be whatever. Spins, assets when I did econophysics, or concentration, whatever. But no, never double dot equal force. So what does it bring us from this equation to this equation? Okay, so this is a bit more specifically Newton's law. There is a mass. Okay? This is the first step that you have to take to throw away the inertial term. So you say, yes, mq double dot equal force, but there will be some dissipation. And again, there's always some dissipation and some noise, okay? And dissipation is closely related to noise. Dissipation and noise, they're just two different sides of the same coin. This was the big intuition of Einstein of the fluctuation-dissipation theorem. So this is our way to put a lot of information that we ignore under the rug. So yeah, dissipation is a complicated thing. This interaction with the heat bath, we don't know how to model that. And noise, well, also noise is not noise. Also that is interaction. So, but let's model this with these two numbers. One which, slows you down, dissipation, and the other one which heats you up, noise. But these are the same things. It's interaction with the heat bath. Okay, so the reason why the particle slows down with an inertia is also the same reason why it shakes around. Okay, so now let's do some dimensional analysis in order to avoid the whole calculation. So this term here must have the same physical dimension as this term here. Otherwise, I make any mistake. So this means that there is an extra time derivative here. So this means that m over t must have the same dimension as eta. So you immediately see that in order to have this guy much smaller than this guy, you need to have m over t much smaller than eta, which means time much larger than m over eta. Again, I apologize, this is very basic statistical physics, but it's useful to revise it. So this is the natural dissipation timescale of the system, the ratio between inertia and dissipation. So what this is telling you is that for long times, for long enough times, you can throw away this piece, you carry this on the other side, and you get this equation. Then you also rescale time, you can set e equal to 1, but forget about that. So this is the way you go from Newton's law to this overdamped Langevin equation, which makes sense. So we all know that for long times, dissipation always dominates over inertia. So after all, who wants to study transit? Because the whole point here is that, yes, you have a transit where m over eta is still there, but if you wait long enough, then you can throw away this. And we don't want to study transits, we only want to see the asymptotic behavior. And if you add space to that, so if you now treat a field and not only coordinates, it's the same thing for long distances. So in the long time and the long distance limit, which is also called hydrodynamic limit, you can throw away all inertial terms. Because who is interested in transits? Well, perhaps we are interested in transits. Because information transport across a finite system like that is all about transit. We don't have the infinite time limit. Information must spread very quickly across the flock to change direction. The system is finite. It's a few thousand birds, a few hundred birds. So we are far from the hydrodynamic limit. So throwing away inertia, probably a bad idea. So we have to reinstate inertia. How do we do that? Well, it's not that straightforward because our coordinate here is not space, so inertia will not be the mass. It's the phase, it's an angle. So one may think that inertia is a moment of inertia, the angular moment of inertia, but it's not even that. This is a very generalized coordinate, okay? So we have to be careful. What kind of inertia are we talking about here? So let's use symmetry to guide us. Again, standard mechanics here. So we know that symmetry, conservation laws, Poisson brackets are all very deeply connected concepts. For example, translation. So translations are parameterized by Q, real displacement, and they're generated by P. So every symmetry has a generator and a parameter. Okay? In the case of spatial translation, these are Q and P. In the case of time translation, those are T, time, and energy. Okay? So the fact that P and Q are the parameter and the generator of the symmetry is clearly expressed by this Poisson bracket relation, telling you that the derivative of anything, A is whatever, with respect to Q, to space, is the Poisson bracket of that thing and the momentum. So the generator of space translation is linear momentum. This is why, if the system is invariant under translation, you have conservation of the momentum. This is Noether theorem. Okay, so from that, this equation follows. Q dot is equal P over M, and P dot is equal to the force. So, you see, the first equation is telling you that the generator of the symmetry rules the time derivative of the parameter. And this is the inertia. This is the definition of inertia. It's that coefficient between parameter of a symmetry and generator of the symmetry. Another symmetry, rotations. So rotation, normal rotation in the external space, okay? So the parameter is theta, so your angle with respect to a common origin of, let's say, all birds, for example. And the generator is angular momentum, and you have exactly the same kind of relations. So you have theta dot equal L over I, and L dot equal the force. In that case, the force would be the torque. But again, we have the inertia here, which is the moment of inertia, which is something different from the mass. It's the equivalent of the mass in the rotational context. So can this be our case? No, it cannot. And this is a very important point. If you take a bunch of points and you rotate all of them with respect to an external origin, what you get is parallel paths of rotations. So the internal guys will have a very small radius of curvature. The faraway guys will have a very small, large radius of curvature, sorry, the other way around. Birds close to the origin will have a very small radius of rotation, so very steep rotation. These guys will have a very small radius of rotation. So their centripetal acceleration will be very different. And also their velocity, their speed should be different. This guy must run much faster than this other guy. So this parallel path kind of rotation is not the one that birds use. They use equal radius rotations. So they cross their path, but with the same radius of curvature. Because this is the only way you can rotate a system with the same speed. So this is not a way a car rotates. Okay? A car, the internal part, rotates at a different speed than the external part. But the points in a biological system, you need them to have the same speed. So you cannot use this kind of rotation here. So what you need to do is to really rotate the order parameter, which is called an internal rotation, in the space of the order parameter. So this is the phase. The phase is the parameter, not of a rotation with respect to the external origin, but of the velocity itself. So now, if you have the two birds, and you rotate both by the same amount, but the velocity, not their positions, then you get the right kind of rotation. Okay? So the parameter is phi, so there must be a generator of that. So what is the generator of the rotation in the space of the order parameter? Well, there is not a word for that in biology, but in quantum mechanics it's called spin. Okay? So S is really has the same role as a quantum spin. It's the generator of the rotation of your order parameter. And so what you must have is that phi dot is not equal to the force, but is equal to the spin over some inertia. What is it? We don't know. It's an effective parameter telling you how much birds resist in changing their radius of rotation. And then the force is acting on the spin. So we unwrap this equation here. So F dot is no longer the force, but F dot is equal to S over chi, and S dot is equal to the force. All these three numbers are the inertia, but they're very different kind of inertia. M and I are real mechanical inertia, while at this level, everything here is generalized. So chi is some sort of behavioral inertia, call it as much as you want, but it's not the mechanical inertia of the bird. It's not the mass. So then from this equation, okay, you go to this pair of equations. Now you reinstated inertia. Okay, so the force is acting on the spin, on the generator, and the spin is acting on the phase. So this is the spin, this is the inertia, and now you take a second derivative of phi, and you get this equation. And now you have solved the problem, because this is just D'Alembert wave equation. Second derivative in time and second derivative in space. So the dispersion law of this is the good old omega equals ck, so linear propagation of waves, which is what we have. Well, this seems a bit far-fetched because we're using Hamiltonian Poisson description to describe very dissipative systems like birds, but it works. So let me go back to this. This was the classic theory, so no inertia. Okay, again, it doesn't work very well. And this is the new theory. So the only difference between these two simulations is the presence of inertia. Okay, so this is exactly what they do.
Sorry, what happened to the dissipation?
Good point. This was a highly simplified version of the thing. We also add here dissipation and noise, of course. And as long as dissipation is smaller than inertia, you have that kind of behavior. So the good things of this model is that when you add the dissipation and noise, you have as a limit the original model. So the Vichet model is the overdamped limit of this inertial model. And so you have all the regimes. If inertia is strong with respect to dissipation, you have linear propagation. Otherwise, you have diffusive damping as in the Vichet case. Yes, you must have dissipation and noise here. So you must add a minus eta phi dot term here plus psi. Okay, so again, this works, it's very nice. There is something more. Is it me? Yeah, there is something more. The theory also makes a prediction. So you remember, we didn't understand why the speed of propagation was different from flock to flock. But now we have an equation, and this is the speed of propagation. So Cs is j over chi. So chi is, okay, we don't know, it's some inertia, probably, hopefully the same for all birds, not necessarily, but j is the strength of the interaction. It's how strongly they want to align to each other. So we can measure j, because j is directly connected to the order parameter, which is this quantity here, it's called the polarization. Would be the magnetization in ferromagnet. It's a number telling you, number defined from 0 to 1, telling you how strongly the system goes in the same direction, okay? In the spin wave limit, there is a very simple relation connecting phi to j. So you see, if j is very, very large, phi goes to 1. This is basically what you need to know. So you invert that, so if you measure phi, you have j. And measuring phi is easy for us because we have all the velocities. So then we have an estimate of j in all our flocks. And so this equation is telling you that the speed of propagation goes like 1 over the square root of 1 minus phi. Something we could hardly guess before. Also, phi is a dimensionless number, so it was not easy to guess this relation by mere dimensional analysis, which is normally what physicists do, by cheating. This must be the law. Yes, dimensional analysis. Now this is not the case. Phi is the dimensionless quantity. So this is the prediction of the new theory. And these are the data. So there is a clear outlier. Okay. But it works very well. Again, this is not a completely trivial dependence on the polarization. So each one of these points is a flock. So these are 12 flocks in 4 years. Not very efficient way to publish papers, but it works. Okay, so final biological message. Why then many biological groups are so strongly polarized? So one may say, otherwise they will bump into each other. Well, not true. The packing fraction of flocks is actually pretty low. They seem very dense because it's a two-dimensional projection of a three-dimensional thing. But actually they're, quite spaced between each other. So why they go so much so in the same direction? Well, what we predicted is that the speed of propagation was like 1 over square root of 1 minus phi. So the larger it's phi, the quicker is the propagation of the signal. So this is actually what you mean when you say, close ranks. So by going in the same direction in a more accurate way, you increase the speed of propagation of the signal across your system. And this is important because the moment when a wavefront is crossing the system is a very delicate moment, because it's a moment where half of the system is going in one direction and half of the system is going in the other direction. So if you lose coherence, it's exactly in that moment. So you want that wave to pass as quick as possible through your system. So this may be the reason why polarization is so large in this system. So final message. Inertia is very important to transfer information across a biological network. You can't do that if you have an overdamped equation, and despite the fact that you have to find a balance, of course, because too much inertia means that the signal will travel very slow. But if you don't have inertia, you don't have any linear signal at all. And these are the people in my group, youngster here, and these are my senior collaborator, Tomás Grigera in La Plata, Irene Giardina in Rome, and these are the birds. Thank you very much.